Welcome back to the second session of this season school. So for this second talk, we are happy to listen to Jeremy Booher, who comes from the University of Canterbury. Is that right?
Yes.
And he's going to tell a lot of incredible things about zeta function of curves and about the Weil conjecture. So it's up to you now. Thank you very much for coming here.
It's my pleasure. Thanks for organizing this. And I hope everyone has a good time. I was asked to speak about something in number theory and then given some vague guesses about the background of the audience. So I decided to talk about some big ideas in number theory that really come from algebraic topology and algebraic geometry. And then how those ideas, which you might not see if you're just focused on sort of doing computational things, nevertheless are quite interesting in terms of informing what kind of computations you could do. So I hope everyone can find something they like. All right, so the first thing I want to talk about is zeta functions. So if I have a variety over a finite field, f cubed, what we want to study is the zeta function, and one viewpoint is that it's a sort of a combinatorial generating function, some sort of generating function for the number of points on your variety. So it's the exponential of the sum from n equals 1 to infinity of the number of points on your variety over fq to the n times t to the n over n. Okay, so let's see an example of this. A nice simple variety is projective space. So the first question we have to ask is, how many points are there on projective space over a finite field with q to the n elements? Well, this is n plus 1 tuples of elements of f q to the m, so it's f q to the n times m minus 1, because we don't want the tuple of all zeros. And then they're up to scaling, so we divide by q to the n minus 1. And then I need to go change this because I said it was m plus 1 tuples, so let's change that. And then when you divide, you get a nice expression involving powers of q to the n. So we can put this into the definition of our zeta function, and it's more convenient to look at the log of the zeta function, forget a nice simple expression for now. Well, that's going to be the sum from n equals 1 to infinity of these point counts. So 1 plus q to the n plus q to the 2n plus q to the m plus 1 times n times t to the n over n. This one doesn't have the m plus 1. And then we can regroup these to have a sum from m equals, from let's say j equals 1 to infinity to m of q to the j times t all to the nth power over n. And then you'll recognize that that's a power series for log. In particular, you end up with the sum from j equals 1 to the m of negative of the log of 1 minus q to the j to the tth power times t. So what does it say about the zeta function? Well, it says that the zeta function for the projective space is 1 over 1 minus t times 1 minus qt. Keep doing that up to 1 minus q to the mt. So we end up with this nice rational function that encodes information about how many points there are in projective space over fq and its extensions. Okay. Let's try a little more complicated example. Let's try an elliptic curve. So a very important piece of information is what's sometimes called A of E, and it's Q plus 1 minus the number of points on your elliptic curve mod Q. So it turns out that if you let alpha and beta be the roots of the quadratic t squared minus A of E t plus Q, we'll show that the zeta function for our elliptic curve is 1 minus alpha t times 1 minus beta t over 1 minus t times 1 minus qt. So it has the same sort of denominator as projective space, or in particular as projective line, but the numerator is more interesting, and it encodes information about, again, these point counts in the form of the roots of this polynomial. So before I go any further, I should try to motivate this zeta function, and in particular name, in as many ways as possible. So one motivation is just it's a combinatorial generating function for point counts. But there's another motivation which comes from algebraic number theory in its connection with the Riemann zeta function. So this connection is going to be clear if we establish a sort of very simple lemma, which says if x is a variety over fq, I can write this zeta function as a product over points of x. The product is the product of 1 minus t to the degree of x inverse. And here, the degree of x is the degree of the extension of the residue field of x over fq. So really you should think that that's just what kind of extension of your finite field do you need to make in order to have the coordinates of your points be defined over that field. Okay. And so if you wanted to prove this, I'll just sort of sketch it. So x is some point in x. So this appears as a point defined over f q to the n, if and only if the degree of x divides n. So you should think that if your point was defined over a quadratic extension, it'll appear in all of the even degree extensions of f cubed, but it won't appear, for example, in fq cubed, because that's disjoint. It's an extension of f cubed. So that's completely sort of simple. And then you just formally manipulate the power series for the log of the zeta function. And you just group contributions for each point in x. Okay. So you have to write down a few details, but it should not be a surprise that you can do something like this and you get the same sort of logs we were seeing in the example for projective space. And this lemma pops out. So why is this lemma a good motivation? Well, if I substitute q to the negative s for my formal variable t, I end up with a product for points in x of 1 minus the size of the residue field of x to the negative s power, and then the inverse of that. And you take a product for all the points of x. Well, the Riemann zeta function has a very similar expression. zeta of S is the product over primes of 1 minus p to the negative s, and then multiplicative inverses. So of course, the size of the residue field of the prime ideal p in the integers is p. And so this is running over primes of spec z. So this looks very similar. And in fact, if you like schemes, you can define a zeta function for any scheme of finite type over the integers, and then the Riemann zeta function literally is the same type of example as these zeta functions for varieties over finite fields. By the way, the zeta function usually is written as the sum from n equals 1 to infinity of n to the negative s. That's probably what you've seen first if you're just sort of passively familiar with Riemann zeta function. But you can get this other product using unique factorization. Okay. So the Weil conjectures are about zeta functions. So let me tell you what these conjectures say. Okay. So the idea is that X is going to be a smooth, projective, geometrically irreducible variety over a finite field FQ. And let's say the dimension of X equals M. There are sort of three main parts of the Weil conjectures that I want to talk about. The first is rationality of the zeta function. And that part of the conjecture says that the zeta function of X is a rational function. And in particular, it has a very nice sort of form where you have a bunch of polynomials on the top and bottom. And you know that the zeroth polynomial is 1 minus t. The largest one is 1 minus q to the mt. And furthermore, all of the polynomials have integer coefficients and have constant term 1. Okay. The second piece is the functional equation. So there's supposed to be something called chi, which is like an Euler characteristic, which is -1 to the degree of pi. And you sum from I equals 0 to 2m. And the functional equation says that there's some symmetry, that if you take the zeta function and evaluate at 1 over q to the mt, up to a sign, you get a power of q, depending on m and chi, a power of t, depending on chi, and the original zeta function evaluated at t. And then the third important piece of the Weil conjectures is the Riemann hypothesis. And that's that the roots of these polynomials pi of t occurring in the zeta function have absolute value q to the negative I over 2. Okay, so those are the three sort of important parts of the Weil conjectures for what we're going to talk about today. There's another part which I'm going to ignore. So let's go back and look at our examples and see if these are true. So let's think about the projective space. The zeta function was this product And then you look and you see, well, this is P0, this will be P2, and so forth, and this will be P to the 2m. And there aren't any of the odd P's that would be showing up in the numerator. They're all 1. So the Euler characteristic is going to be m plus 1. And very good, we have this rational function. And then you can do a little computation to see that q to the m chi over 2 times t to the chi times zeta of the zeta function is, well, looks almost like this. I'm going to write it slightly differently. I'm going to write it as 1 minus t over t times 1 minus qt over qt all the way up to 1 minus q to the mt over q to the mt. And so if you keep track of things, that's accounting for all of the terms in front. With these terms I've been adding to the denominator. And then you just simplify things and you end up with 1 over 1 minus, I should do it the other order. T minus 1 there. 1 over t minus 1, there we go. 1 over qt minus 1. Okay. There we go. And that's basically the zeta function. There's some signs that you need to keep track of. And the other thing is to note that sorry, the signs, that's the one thing to keep track of, but we had a plus or minus sign. I didn't tell you anyway, so it all works. So we have, so again, we have the this functional equation. And finally, there is supposed to be this Riemann hypothesis that the roots of these polynomials have absolute value q to the negative I over 2. Well, you can see that just by looking at the denominator, and you have no q's, then you have q in P2, and you have up to q to the m in P to the 2m. And so that makes the roots have the right absolute value. It's very simple, and there's nothing in the numerator. So the Riemann hypothesis is true for the projective space. All right. Now let's look at our elliptic curve. Remember, the zeta function of the elliptic curve had the form 1 minus alpha t, 1 minus beta t, and the denominator was 1 minus t times 1 minus qt. So elliptic curves are one-dimensional, so m is 1. If you look at the degrees, you end up with the Euler characteristic being 0. And remember that alpha and beta are roots of some polynomial. So in particular, we know their product was q, and their sum was the sort of modified point count a of e. All right, so let's start at this. It has the right form, it's a rational function. The numerator is P1, this is P0, and this is P2. You can check there's a functional equation using a similar sort of technique as we used for the projective line. It works out. So what does the Riemann hypothesis say? Well, again, there's very simple things on the denominator which satisfy the Riemann hypothesis because of that, the 1 and the q. But what's really interesting is on the top. The roots of P1 have absolute value q to the negative 1/2. So that implies that the absolute value of alpha and beta are both q to the 1/2. And so because alpha plus beta is a of e, which equals p plus 1, q plus 1 minus the point count of the elliptic curve over fq, the Riemann hypothesis implies the Hasse bounds on the number of points on the elliptic curve. All right. So we looked at a projective space. We looked at an elliptic curve. Let's look at an almost example of the Weil conjectures. So this is an almost example because it's not literally true and we can't prove it. But let's talk about what's going on. So this would be for the integers. In other words, for the Riemann zeta function. So there, we had our parameter t, but we were thinking of that. We were taking maybe q to the negative s to make things look more like the Riemann zeta function. And we were also looking at 1 over qt, which would be q to the negative 1 minus s. And so what would the sort of analogy with the Weil conjectures predict? Well, it would predict that the zeta function is a rational function. Well, that's not quite true. It's a complex valued function and it's meromorphic. We'd also expect a functional equation. That relates it to the zeta function at 1 minus s. And we would expect a Riemann hypothesis. So the roots of, say, the P1 of t have absolute value q to the negative 1/2. That's what the expectation is based on this analogy. So what does that say? That says the roots of P1 to the q to the negative s have the real part of s being a 1/2. That'll get you the right absolute value. I.e., you sort of expect the non-trivial roots of the zeta function of s have the real part of s equal 1/2, which of course is the sort of classical Riemann hypothesis. Now, of course, everything I've told you is like completely ludicrous. Like the motivation for the Weil conjectures came from algebraic number theory. So going backwards to predict things about the Riemann zeta function is completely ahistorical. But I hope it sort of gives some motivation for some of you who have a background in algebraic number theory about where these geometric conjectures are coming from. All right, have people accumulated questions they want to ask? This is a good point to pause if you have any. All right. All right, so we talked a little about what the conjectures are. I want to give some history now. So in 1949, they proved the Weil conjectures for curves. And he formulated the general conjectures. Okay. And so he was sort of generalizing stuff which had been sort of in the air for the last, up to, in the first half of the 20th century, originally about function fields, trying to do the same thing in function fields you do in number fields, and then recasting that into geometric language. That's what he was sort of doing. And so this is building on work of people like Artin and Hasse. But his motivation for this wild generalization, from function fields to curves to all varieties, came from cohomology theories. Okay. And so the idea is a sort of nice variety over the complex numbers of dimension m has cohomology in dimension 0 to 2m. So this is like the topological cohomology, like singular cohomology. And there was a famous result called the Lefschetz fixed point formula. So if you could apply it to the Frobenius map, which is something in characteristic P, and you had some version of this which worked, it would give you that the zeta function of your variety X is a rational function of exactly the form you see in the Weil conjectures. And these polynomials would be the action of 1 minus the Frobenius times a formal parameter t on the ith cohomology group. So if you had some sort of cohomology theory which would let you actually make this precise, you would get the first part of the Weil conjectures, the rationality of the zeta function, for free. So as sort of an example, without actually having any precise details, for an elliptic curve over FQ, what do you expect? Well, this 1 minus the Frobenius times t, how should it act on H0? Well, H0 is supposed to be like the number of connected components, which is 1. And this should be doing nothing to that. It's not changing it. So it should just look like 1 minus t, because the Frobenius is doing nothing, and then you have 1 and you have the minus t. What should happen on the second cohomology? Well, you sort of learn in algebraic topology that a degree n map multiplies the top cohomology group by n. So Frobenius is like the qth power, so it should have degree q. So you're expecting 1 minus qt. Now, what about on H1, the first cohomology? Well, that's a little more mysterious. It turns out that the tape module, the analytic tape module, is a substitute for the H1. And if you know anything about elliptic curves, and you start learning about this, you'll eventually learn that 1 minus the Frobenius at q times t acts on this tape module okay, now the problem is I have this backwards from the other thing. going to be 1 minus alpha times t times 1 minus beta times t. Okay, so that's some computation you might have learned about, and I may talk about at the end if I have time, about how the Frobenius acts on the Tate module, an elliptic curve. And it turns out to be exactly related to these alpha and beta we were seeing earlier as the roots of that of the polynomial t squared minus a of et plus q. And so from these predictions, then you get exactly back what we actually computed the zeta function elliptic curve is going to be. We're going to have these two simple factors, the 1 minus t and the 1 minus qt on the bottom, because they're the 0th and 2nd cohomologies. And then we're going to have on top this contribution from the H1 in the form of the Tate module. Okay, so simply being able to sort of have this cohomological interpretation sort of starts to explain some of the shapes of the zeta functions we're seeing, and it would actually prove the rationality statement, assuming you had enough theory to make sense of this. In topology, there's also something called Poincare duality. And that's a relationship between the ith cohomology and the 2 to the m minus ith cohomology. If you write down what this means and sort of plug it into your expectation, this just gives you the functional equation for free. All right, so we were talking about motivation. We talked about the rationality and the Poincare duality coming from these algebraic topology, algebraic geometry ideas. On the other hand, the Riemann hypothesis is just motivated by algebraic number theory. And so, in fact, for many people who work in number theory, the strongest evidence that the Riemann hypothesis is true is the fact that these analogs in algebraic geometry, in the form of the Weil conjectures, have been proven. So of course, now there's this little problem that it's really not possible to make precise a lot of what I said, at least according to what they knew. So they was speculating that there'd be some cohomology theory which would make everything work. But he didn't know what that was. So Serre, sometime in the 1950s, started to think about this, and he proved an analog of the Weil conjectures for a type of manifold called Kähler manifolds over the complex numbers with a map that looked sort of like the Frobenius map does in characteristic P. So it's some sort of map of degree Q, which has some nice properties that makes it sort of behave sort of like you'd expect. And then using standard and very standard things about the cohomology of Kähler manifolds, or just really any sort of variety over C, then he was able to prove the sort of analogs of the rationality of the zeta function and the functional equation. And then with a little more work using Hodge theory, which is a sort of a non-trivial thing, but he used it, you can get the analog of the Riemann hypothesis for these Kähler manifolds with maps which look like the Frobenius at Q. So that was trying to make precise sort of Weil's intuition that, you know, his conjectures should have something to do with cohomology. And then in the 1960s and 70s, Grothendieck and lots of other people who were sort of reformulating algebraic geometry in terms of schemes were working on what is this cohomology supposed to be. And eventually, they developed a theory of cohomology called étale cohomology. And this is something that works for varieties over a finite field, but is like a topological cohomology theory, like you might see for a manifold. In particular, then you can literally make sense of what does it mean for the Frobenius at Q, which is some endomorphism of variety, to act on the ith étale cohomology group with some coefficients, maybe like the integers mod L. Now you really only want to do this for primes L which don't divide Q. And you can sort of take variance where you use maybe L-adic coefficients as well. And so Grothendieck and everyone working with him started studying this, and they proved a bunch of results which said this behaves just like the cohomology theories we're used to for manifolds. And then those immediately give the rationality in the Weil conjectures and the functional equation. And so this is a real proof now because you've done all the hard work and developed this étale cohomology theory. And so the Riemann hypothesis was harder. It's a consequence of some conjectures Grothendieck made called the standard conjectures. Which would allow you to adapt Serre's approach using Hodge theory to work for étale cohomology. But this didn't work out. And in fact, even to this day, we don't have proofs of all the standard conjectures. And instead, Deligne finished things off in 1974. He proved the Riemann hypothesis part of the Weil conjectures using a different technique which avoided the standard conjectures. Okay, so I just told you a really big story. What does this have to do with number theory, or even more particular, like algorithmic number theory? Okay. So I just want to sort of make a case that even just sort of understanding these ideas exist can help sort of understand the broad picture of what's going on and what might be possible. So I'm going to talk about zeta functions of curves and what you can do with them. So one thing you can do is think about point counting on elliptic curves. So again, we have an elliptic curve over a finite field of Q elements. The sort of goal is to compute the number of points on E over, say, FQ. And so there are various things you could try. You could just try sort of picking some equation for elliptic curve and then plugging in different values of X and trying to solve for Y and seeing when the value of Y you get is defined over FQ. But you can do much better than that. There's an algorithm due to Schoof that does this in polynomial time. That's very nice. And then there's a very simple idea and then a bunch of details. So the idea is you want to compute the zeta function of E. So really you just want to compute the numerator, P1 of T. And just try to compute it mod L. So that boils down to looking at a quadratic polynomial like this, mod L, and try to figure out what this is for some small primes. Well, this is the action of 1 minus the Frobenius on the if you want it mod L, it's like it's on the action on the first. This is on the first cohomology group with coefficients mod L. Of course, now you don't want to actually do that because you can't compute with étale cohomology. But you replace this with the L-adic Tate module. Or really, if you just want mod L, you just work with the L torsion on your elliptic curve. And of course, all our understanding about these cohomological ideas says, yeah, well, the zeta function, these point counts, you should really just be looking at how the Frobenius and sort of combinatorial generalizations of that acts on the cohomology groups. And then you sort of make it concrete so you can actually do computations by looking at either the L-adic Tate module or more simply just the L torsion. And then you figure out that yes, you can do this for a bunch of small primes L. And then use the Chinese remainder theorem to get A of E, which is giving you the point count, because we know how large it is using the Hasse bound. Okay. So I expect some people have seen this idea before and have probably seen like the actual details of how you do these computations efficiently. But I want to just sort of say something more about the broader perspective. We were trying to use cohomology, and we were using primes L, which were, different than the residue characteristic of our finite field. Why were we doing that? Well, that was just because of what Deline had available when he proved the Weil conjectures. People have done more work. And you now have p-adic cohomology theories. So if the characteristic of FQ is P, and then we're going to imagine that P is small and fixed, there are faster methods to compute the zeta function and hence the point counts based on p-adic cohomology theories. These are different than étale cohomology. Étale cohomology doesn't like using coefficients that are like Z mod P coefficients when you're in characteristic P. But you can work harder and come up with other things which let you do this. And these are really nice because they work for things beyond curves. And they're faster than sort of the analogs of Schuf's algorithm. And so this sort of approach is due to many people, but it's inspired by Dwork's proof of the rationality of the zeta function. Which was done independently of what Grothendieck and Deligne were doing. And this was using p-adic analysis. And then, so that was quite a while ago. And then over the next few decades after that, ideas percolated and people developed more and more powerful p-adic cohomology methods. And then people realized that yes, you can do the same sort of point counting using these other methods. Okay. And finally, I wanted to talk about another reason you might care about zeta functions and computing with them, is because you can use them to factor polynomials over finite fields if you know lots of other things. So now I want to think about a family of elliptic curves. So there's a parameter S that I can change. And we're still over FQ. Now suppose I have some polynomial, f of s, and for simplicity, I'm going to assume it's just a quadratic with two roots, R1 and R2, which are both in FQ, but we don't know them. I mean, when I try to compute them. And as far as I know, even in this sort of relatively simple example, it's actually not known how to do this in deterministic polynomial time. There are lots of perfectly good randomized algorithms which you can use, and you can compute anything you want, but it's not possible. No one knows how to actually do this deterministically. So I want to suppose that I take the zeta functions at these two specializations, so at R1, and suppose that's different than the zeta function when I specialize at R2. So what happens if we use Schuf's algorithm? But instead of like actually working over a finite field, we work over FQ adjoin T mod this polynomial f of t. So this is not a field because f factors over FQ. Well, as with many things, if you sort of pretend you're working over a field, things will work for a while, and then at some point, things will fall apart because you're not over a field. But the way things fall apart will give you factors of f of t. The reason it's failing is because these two specializations of your elliptic curve have different zeta functions. And so if you try to compute the zeta function, you can't get an answer because it has two contradictory answers. And luckily, the way it fails, again, lets you actually factor your polynomial. And so you can sort of take more general factoring problems and reduce it to this sort of simple example. And so Kayal realized that if you could guarantee that each member of your family, each elliptic curve in your family, had a different zeta function, you could factor polynomials over finite fields in deterministic polynomial time. And then Poonen realized that there's a variant. You could also use higher genus curves if you use a generalization of Schuth's algorithm due to Pila. And so the reason, sort of the backwards reason of why I chose this topic for this talk was that some of my work with Felipe Bolak here is sort of aimed at trying to understand sort of how to distinguish curves based on their zeta functions. Okay. So nothing we've been thinking about helps for this question of factoring. So by distinguish, that's a good question. So maybe the simplest thing would be to say is if the zeta functions of two curves are being equal, that's the same as the Jacobians being isogenous. So that tells you some relationship between the curves, but it doesn't say they're the same or exactly the same. You could try to use stuff like the Hilbert class field or other natural covers of your curve. And in particular, their zeta functions. And then you're hoping like, well, if I have two curves and their zeta functions agree, and then I look at some natural covers and the zeta functions of those things agree, can I sort of get enough of that data to actually say the curves are the same, like isomorphic? And then that would mean then you actually have some criteria based on zeta functions and related things to tell apart curves. And if you imagine a very strong version of this, you could then take a family of elliptic curves. Probably wouldn't work for elliptic curves because there just aren't enough possibilities for the zeta function, but you could use a family of higher genus curves. You could arrange that each member of the family is distinct, so there are no isomorphisms between members of the family. And then if there is enough, if you can compute enough of these zeta functions that would simultaneously be computable and be enough to distinguish the curves up to isomorphism, that would give you a family you could use in Kayal and Poonen's proposals for how to factor polynomials. Now, nothing we've done is actually of any computational use because we're just thinking about Hilbert class fields and other things which are very large, have big genus, and so you try to compute and then you're like, okay, that doesn't actually work, even for like a theoretical question without some motivation. And so I think this is a good time to stop. I'm happy to take more questions.